Here's an example of using nearest neighbors for digit recognition, and this is one of the success stories for the algorithm. So here the input is we get 16 by 16 bitmaps. We're assuming that each pixel is a gray level, let's say 8-bit grayscale value. And what we need to do is we need to compute distances between a testing image, a testing bitmap A, and a training bitmap B. You can do it in a very, very simple way if if you do some preliminary computer vision magic on this. So if you deslant them and normalize them and box them to about the same size, then you can use just the straightforward Euclidean distance to measure how similar or how dissimilar the bitmaps are. So it would look like that. You are summing up over all the pixels, over all the pixel positions in each bitmap. So I'm summing up over all the rows and over all columns in each row, and I'm taking the value of the pixel in row R, column C for image A, subtracting the value of the same pixel in image B, squaring it, adding it up, taking the square root. Just your normal Euclidean distance between the two bitmaps. Okay? Now, once I've done that, once I've computed the distance between the testing image A and all the training images B, what I do is, for a testing image, I find a certain number, let's say 7 nearest training examples, and then I look at the most frequent class, at the most frequent digit label in those 7 training examples. So if you do it, you get results that sort of look like that. So if these are your test images, that's a 0 and a 2, these would be the 7 nearest neighbors according to just a straightforward Euclidean distance between the bitmaps. So you get a bunch of things that look like this 0, you get a 6 at the end. Right? And then you do classification. You look at these 7 examples. These will be labeled with a 0. This will be labeled with a 6. So the dominant class, the class that gets 6 votes, will be 0. So you'll predict a 0 for this bitmap. For this bitmap, you have a tie. You have 3 examples voting for 2. You have 3 examples voting for 8. So you're going to break that in some way. And a typical breaking strategy is you look at you back off to one nearest neighbor in this case. So in that case, that would actually be classified as a 2 as well. 4, you would get it perfectly. This 4, you would actually misclassify it, just like you would misclassify this 9. Right? This 9 has a lot more 7s, so you would classify it as a 7. But this 4, you would classify it as a 9, assuming that that thing is a 9. Right? The first example, it kind of looks like a 9, but it also kind of looks like a 4. So I don't actually know what that is and whether this would be classified as 4 and a 9 or as a 9. So it's a very simple algorithm. The accuracy that you get is extremely impressive for such a simple algorithm. So on the MNIST task, with a 7 nearest neighbor with Euclidean distance, you can get 95.2% accuracy. And the best that you can get with an SVM is 95.8. Really impressive performance, considering how simple the algorithm is. It's particularly impressive if you realize that humans are not perfect on this task. So humans only get about a 97% accuracy on the task of recognizing digits. So humans make mistakes, right? It's digits like that, the one where you can't tell whether it's a 9 or a 4, that's causing problems. So 95.2, that's really, really impressive.